exists this delta. Consequently, if y is an element of the ball of radius delta centered at x, that means y is an element of the inverse image of this, which is to say that if the distance from x to y is less than delta, that means y is an element here, right? That implies that f of y is an element of this ball, which implies that h of f of x to f of y is less than epsilon. So there you go. That's this is an if and only if proof. I just gave you the forward implication, but I'll let you sort through the reverse implication, right? It's almost already here, I think, but so basically we just have to sort through the notion of neighborhood, and here's a picture of what just went on. Maybe it's helpful. So like I'm starting with the neighborhood of f of x over here. I'm looking at its inverse image. Now the inverse image of this ball, it doesn't have to be a ball, right? Just because f is continuous at that point doesn't mean the inverse image of a ball is a ball. It could be something funky like this, wee, like this, whatever this is. But the thing is that this is an open set, right? And in the metric topology, that means every point's interior. Well, x is a point inside the inverse image of that, which means that there exists this ball of radius delta in there, right? But then when you take a look at what you got, if x is an element, if y is an element of that ball, that means the distance from x to y is less than delta, and that implies that that over here, the image of this thing, it fits somewhere inside that, which means that the distance from f of x to f of y is going to be less than epsilon, because this is like epsilon distance. So anyway, yep. Oh, I seem to be in the second hour of this lecture. Sorry about that. I try to keep these under an hour for my various reasons, but here we go. All right. I think what I'm learning here is I really should have split the metric space into 2 lectures, huh? If I was in a classroom in a 3-hour format, I'd be in trouble with this material. Anyway, so here we go. Another example. This is the distance from a subset. So like, a lot of times you're asked questions like, how far is this point right here from this chopstick, right? And so the answer is, well, is it going to be the distance over there? Is it going to be the distance to, like where is it going to be over here? So the natural thing to do is to use the minimum distance, right? But the thing is, sometimes your object is fuzzy, so you don't want to just use the minimum. You use the inf, which is the let's see here. I'm going to say the greatest lower bound. It's not the minimum, but it's the closest to minimum that you can get when you don't actually have the minimum, right? And so greatest lower bound, which will be the minimum if the minimum exists, but it doesn't have to be, right? And then Minetti talks about how this distance on the subset is a continuous function with respect to the distance on the given metric space. And I was pretty confused here because I forgot the cardinal rule of when you're confused, keep reading. But then, so like if he claims that at the start, he claims that the absolute value of the distance from z to x minus the distance from z to y is bounded by the distance from x to y. So if you know this implies the continuity of the d sub z metric. And this is not obvious. Like all of these things below prove that, all right? So, you start out with noticing that the distance from z to y minus the distance from z to x is less than or equal to the distance x to y. I mean, you want to show that. That's not obvious. I'm still unfolding it here. So what we do know is that the distance from z to x plus some epsilon is going to be greater than the distance from x to z for all z and z, right? Because this is supposedly the inf, and this is a property of the infimum of a set. You can take the infimum of a set plus epsilon. It's going to be greater than or equal to anything you're finding the infimum of. Well, you can, for any epsilon greater than 0, you can find a z such that this is holding, all right? Anyway, So then you get this inequality. And then rearranging that, you get the distance from z to, sorry if it's not in frame here. Distance from z to y minus distance from z to x is less or equal to epsilon plus this. Then he says you let epsilon go to 0, and lo and behold, you've got that the distance from z to y minus the distance from z to x is at most distance from x to y. And then, so then if you look at that, that allows you to get back to what we were claiming at the start up here, you know, which then proves that the distance function to a distance from an extended object, perhaps in a metric space, is a continuous function, which is good because why is that good? That's good because if you were trying to prove that a minimum or maximum distance from an object existed, right? If you could prove that the distance to that object was bounded, and you knew that this was a continuous function, then you perhaps could use the extreme value theorem to prove that there is a point in the space which attains that minimum. I think the continuity of the extent of the d sub z has applications to calculating the distance to objects. All right, so anyway. Moving along here, sorry if I didn't do that last bit justice. I'm starting to get tired of this section at this point. Full disclosure, you know. So there's a corollary to the epsilon delta theorem, which is this. It says let d and h be distances on the set x. The topology induced by d is finer than the topology induced by h if and only if for any x and x and any epsilon greater than 0 there exists a delta such that the delta ball centered at x is, you know, well, if y is d distance, at most d distance delta from x, then y is is going to be less than epsilon, is going to be less than h distance epsilon from y. Oh, it's hard to verbalize this stuff. Anyway, so I'm going to do the forward implication here. And here it goes. So suppose that x comma d generates a topology finer than that induced by x comma h. All right. So if U is open in the H topology, that means that there exists V open in the D topology, which V is contained in U. All right. So if we look at the H ball set of a radius epsilon equal to U, right? Then there must exist a V which is a subset of that H ball, right? Where V is open in the D topology, which means that there exists a delta such that the ball of radius delta centered at X relative to the D metric is a subset of V, because again V is open, so every point's interior. But then by subset properties, that means that the D ball is a subset of the H ball, which gives us that the distance from x to y being less than delta implies that H distance from x to y is less than epsilon, which is the forward part of this proof. Oy. All right. Conversely, if we have any, if we have that condition that for any x and any epsilon greater than 0, there exists delta greater than 0, such that the distance from x to y less than delta in the d distance implies the distance from x to y is less than epsilon in the h distance, all right? Suppose you know that if you take U open in the H topology and x is an element of U, then there exists epsilon greater than 0, such that there's a ball of radius epsilon centered around x at H, because we're assuming x is an interior point since U is open. And then by assumption, there exists a delta such that the delta ball centered at x is implying that that the distance from x to y being less than delta in the d distance means that the distance from x to y is less than epsilon in the h distance. That's by the assumption. But that implies that y, an element of the ball of radius, delta centered at x, means y is an element of the epsilon ball centered at x with respect to distance h. I've adorned these with sub d's and sub h's to keep track of what I'm saying. So anyway, the ball in the D metric is a subset of the ball in the H metric of radius delta and epsilon respectively, which is to say that the D topology is finer than the H topology, because we just showed that given an open subset in the H topology, there exists a subset, and there exists a open set in the D topology, which is contained in that set. And that's what this shows, right? Because of course, you know, this is, of course, is a subset of 8 of U, right? I guess I should complete the thought. So we have to show that one topology is finer than the other. You take an open set in the coarser topology, and you show that there exists an open set in the allegedly finer topology, which is contained in that. And if you can do that for every open set in the coarser topology, that makes the other topology the finer topology. All right. Menetti's proof is much shorter and probably better. He says that the D topology is finer than the H topology if and only if the identity map from this metric space to that metric space is continuous. So that's probably worth thinking about. And he does call it a corollary to the epsilon delta theorem, right? And I think if you sort through the proof I just made, it does awfully look similar to the epsilon delta theorem I just did, right? So I'm sure that this is the better way to prove it, but I thought it would be good to go through the details here again, because I think you guys are still kind of getting used to what does it mean for a topology to be finer or whatever. Okay, so here we go. Final page. Hooray! All right, so here we go. Sad. It's almost done. All right, so two distances on a set X are said to be equivalent if they induce the same topology. A topological space is metrizable if the topology is induced by a suitable distance. All right. So the thing I got hung up with at the start of the last lecture, start of this lecture rather, the previous video, because this is over an hour, is that it looked like any space, right? Any set is metrizable, right? So like, then what is this definition? Isn't every set metrizable? Well, pay close attention. The topology is already given in this definition. So the question is, can a set paired with a topology, right? Can that be understood as the metric topology for some metric? See, if you already have a topology, as we like to say, it's too late to topologize. And so, hey, there's another place for that joke in this course. All right, anyway, so that's the issue. Is like, yeah, you can put that example 1 metric on any set, but there's no guarantee that the metric topology generated from example 1 metric matches the topology which is already given to the set. All right. So anyway, the problem of metrizability is a well-studied question. Theorems of Tikhonov, Urizen, Nagata, Smirnov, and also Bing, and a host of others. I'm shortchanging dozens of mathematicians, I'm sure, because this was a major focus of topology by certain schools in the early 20th century. Because this really is where the rubber hits the road, so to speak, because analysts think in distance functions, many of them, right? And topologists maybe do, maybe don't. And so if you can prove that everything in topology is really just a distance function in disguise, then in some sense that would have made topology less interesting, because it would have meant that you don't need to do all this weird abstract set stuff. You could just always look at distance functions, right? But that actually is not what happened. It turns out that the concepts of topology are more general than the usual concept of metric spaces. Metric spaces is a large subset of our examples, but it does not subsume all of our examples. In fact, we've already had examples in this course which are examples of non-metrizable spaces. So there is something lost in assuming that your topology is generated from a distance function. Not all topologies are generated from distance functions. So, like I said, let's just give you a quick, and we don't really know all the meaning of all these words yet, but this is of course all from like I looked up the metrizability on Wikipedia. This is like some just footnotes from there basically, but Of course, these things will also be in Minetti if I looked in the future sections, right? This is just a nice summary here. So Urizen said basically that every Hausdorff, whatever that means, we'll talk about that soon, every Hausdorff second countable regular space is metrizable, all right? Urizen actually published this after he was dead, which is a neat trick. But this was published after his death, actually, in 1925. And I think independently, Tikhonov proved it in 1926. So you'll see Urizen and Tikhonov theorems in topology books, right? And then Nagata and Smirnov said X is metrizable if and only if. Notice this is just a necessary condition, not sufficient, right? It's just like, if it's this, that implies it's metrizable. It doesn't say much about the other direction, like when is a space metrizable? Well, and how can I say this? Anyway, let's look at the if and only if one here. X is metrizable if and only if it's regular, Hausdorff, and has a countably local finite basis. So this is 1950 to 1951, and then Bing said X is metrizable if and only if it's regular and T naught and has a sigma discrete basis. When I start reading these two theorems, they sound very similar to me. But anyway, what do these words mean? You know, as we go on, we'll learn some of them. I think it's a little bit too technical for this course, but the point is this is a hard question, whether or not how to describe all topological spaces, right, which are metrizable. That's what Bing's theorem does. So I feel like I might have missed copying something down here, so you should double check me on these things, of course. But anyway, just to summarize and put a capstone to this lecture here, many examples are metrizable, as we've seen. A more exotic example, the group of unitary operators on a separable Hilbert space. All right, so I don't think we yet know what separable means, right? But we'll learn that later. And if you give the Hilbert space the strong operator topology, whatever that means. So I think it's a little bit beyond our course, but one of the selling points of topology is that it does have applications to like operator spaces and more abstract spaces that you haven't even seen yet. There's still many of the things we're talking about topologically have application because of the axiomatic program that we follow, right? But so what are examples of non-metrizable spaces? Which one have we already seen? Well, here they are. The Zariski topology on an algebraic variety, or the spectrum of a ring from algebraic geometry. These are examples of non-metrizable topological spaces. And of course, these are important to a lot of people, right? There's something called the really long line, which you can look up to see how that's constructed. It's complicated a little bit, but it is kind of what it sounds like too. Anyway, that's not metrizable. The Wikipedia article says it's too long. It's too long to put a distance on. So whatever you want that to mean, you can go for it. I'm sure if you follow all the footnotes, you'll come to an understanding eventually. I seem to have lost a C there. All right, spectrum. A topological, this is a little bit less exotic, a topological vector space of all functions from R to R with the topology of pointwise convergence. So pointwise convergence of two functions means that the limit as x approaches the function of f of x is equal to the limit, is equal to g of x. All right, then that would mean that, the limit, I need to think about a sequence of functions, all right? But anyway, let me not get into the weeds here. The point is, pointwise convergence is sort of the naive notion of convergence. You can also talk about uniform convergence and other modes of convergence for sequences of functions. And but anyway, this is interesting that that space is too wild to be metrizable, and that's not that. Well, neither of these is really incredibly difficult to think about. Although I guess the Zariski topology we saw that's a little bit weird. Well, it's weird to me because I'm not familiar with it, but that's because I'm not an algebraic geometer. And then also the R with the lower limit topology, I think we looked at that one. That's the one that takes the basis of like Clopin sets or something like that, if I remember right. So anyway, there are non-exotic examples of non-metrizable spaces. And so we cannot, bottom line is you cannot always give an argument in a topological space talking about distance between points. It just might not be meaningful. And that's really the takeaway message from this lecture is, yes, metric spaces are wonderful. Yes, they are conform to our naive intuition about what we think topology means, but they only go so far. And topology goes past that point, and that's kind of the point. So anyway, thanks guys.